Welcome to today's webinar. The topic today is section properties determination and stress analysis in R section 1. My name is Andreas Hörold. I'm responsible for marketing and public relations in the Dlubal Software company. For instance, the Dlubal website, the German and English webinars, customer projects, etc. I will be the moderator today. My colleague Sonja von Bloor will be the presenter, but my two colleagues can introduce themselves.
Hello, my name is Sonja von Bloor. I provide technical support for our customers, and I'm responsible for the development of the R section program and add-on aluminum design.
And hi from my side, my name is Caroline Lessmann and I work here at Dlubal Software in the marketing department. So I'm responsible for the webinars and newsletters, and I'll answer your questions today.
Okay, thank you for your introduction. You can ask questions via the control panel on the right side of your screen. You can enter a short question here and Caroline and me will answer you. In the case there are too many questions and you don't get an answer during the webinar, you will get an email afterwards. The other way is to watch the entire webinar and email your questions to info@dlubal.com. So to the agenda today, at first Sonja will create a user-defined cross-section using a DXF template. You can see the completed cross-section on the right side. Then she will parameterize the cross-section. Then the third point is calculation and stress analysis, and the evaluation and documentation in the printout report. Okay, then I hand over the screen to Sonja. Sonja, it's your turn.
Okay. The standalone program R section determines the section properties for any thin-walled and massive cross-sections and performs a stress analysis. If you want to design special sections in RFEM or RStab that are not contained in the section library, you can create them with R section. You can then import these user-defined sections into RFEM or RStab. Sections can be generated via graphical or tabular input via importing a DXF file or using a script. Furthermore, a parametric input is possible. Today, I will first show how to create a cross-section by importing a DXF file, and then I will parameterize the cross-section. I import the DXF file via import DXF. Here I have to choose the corresponding DXF file, and then I click on Open. In this window, I can specify the insertion point here, or I can define a rotation, or it's also possible to do a system transformation. The Z coordinate is supposed to be mirrored, so I check the corresponding checkbox. In addition, if there are very short lines in the DXF file, I can minimize the tolerances here if I check this checkbox. Furthermore, it's possible to define the DXF template length units. If I open the drop-down, you can see which units I can choose. I will leave it automatically. Then I go to OK and click also OK, and then all lines will be imported. Then I set the analysis method in the base data dialog. Here I open the base data dialog and I can choose the analysis method. The following analysis methods are available. It's a finite element analysis and the thin-walled analysis. The difference between the analysis methods finite element calculation and analysis of thin-walled structures is a calculation of the cross-section values and stresses on the gross cross-section. With the finite element calculation, the calculation is based on the FE method. When analyzing thin-walled structures, the calculation is carried out analytically. The effective cross-section can be calculated for both analysis methods. A license for the effective cross-section extension is required for this. The green dot here in front of the extension indicates that a license is present. After activating the extension, a standard must be selected according to whose rules the subpanels are to be generated and the effective cross-section is to be calculated. The following standards are currently available: Eurocode 3 Part 1, Eurocode 3 Part 3 for cold form section, and Eurocode 9 for aluminum section. Here I choose Eurocode 9 for aluminum section. The selection of the design method or the standard is irrelevant when using the R-section cross-section in RFEM or RStab. You can select the analysis method in RFEM or RStab regardless of what is set in R-section. Furthermore, the subpanels are generated in the design add-ons based on the standard selected in the design module. I click here on OK, and then I have first to define the material. For this, I open the tree in the navigator data, materials. A material has already been created here. I double-click this material to open the corresponding dialog. I can create or copy another material on the list here on the left. These are the buttons for creation of a new material or copying the selected materials, and I can delete here also the selected material. I can enter the name of the material name directly here in this box. Our section then lists all materials that match that name. If I enter here the name, you can see the corresponding materials. But I can also open the material library for a specific selection via this button. In the material library, filters are available to quickly find the material. I can here choose the material type or the material subtype, the standard, and so on. But there's also a search available in this window. I can directly type in the name of the material, and I choose this material and click on OK. If the material is not in the material library, I can create this material by activating this checkbox user-defined material. If I now go to tab material values, I can define the properties that I want to define. I don't want to do this, so I uncheck this checkbox and I click on OK. After I've defined the material, a part must be defined for the cross-section. This part must be defined for all analysis methods. I create this part by selecting the boundary lines. For this, I go to the navigator data, and then I go to a new part, boundary lines. Then I pick all lines, and then I want to deselect the openings. I hold down the Shift key for this, and then I select the lines that I want to deselect. And then I click on OK. The material is already been defined here. And then I click on OK. After creating the part, I still need to create the openings. I will do this via the navigator data. For this, I right-click on the openings and choose New Opening, and then I select the boundary lines. I click on Apply and Next. Then I select the next boundary lines. Apply and Next. Next boundary lines. Apply and Next. And the last opening. And then I click on OK. For calculation of the gross cross-sectional values using the finite element method, my entries would now be complete. However, I want to make a classification and calculate the effective cross-section, so I also need to define elements. The definition of elements is necessary since the subpanels are only available here. The definition is also necessary for the calculation with the analysis method thin-walled analysis. Based on the elements, some cross-section values such as torsional moment of inertia, warping resistance are calculated if the analysis method analysis of thin-walled structures is selected. If the finite element analysis is set, the gross cross-section values are calculated using the FE method. The subpanels are automatically generated based on the standard selected in the base data dialog. These cannot be changed. If no elements are defined, a cross-section classification in RSECTION and the design models of RFEM or RSTAB is not possible. And it's also not possible to calculate the effective cross-section. In the design add-ons of RFEM or RSTAB, this cross-section is then designed according to the cross-section class 3. I can now graphically create the start and end points of the elements, for example, using the function between two locations. For this, I select the first point and then the next point, and then I can define the distance between the 2 points. I don't want to do this today because it's also a good idea to create the center lines in the CAD application and import them as a background layer. In contrast to the DXF import, in which the complete model is imported, converted into points and lines, the background layers represent a kind of layer for modeling. For this, I open in Navigator Data the background layers. Here, a background layer is already being imported. I delete this because I don't need this today. And then I go here to new background layer. Here I first select the DXF file to be imported via this button, Open File, and I choose the DXF file with the center lines. Then I click on Open, and the insertion point, this is this point here, determines where on the envelope of the background layer is placed at the origin point. I choose +Y here. Furthermore, I leave the origin at the 0 points here, and I define a rotation about 180 degrees. I see the result in the graphic here on the right. And then I click on OK. Now the background layer is imported. Then I go to Object Snaps and I want to control which options are activated. And here the option points, center lines, and focuses are activated. Points is already activated here so that the start and end points of the center lines of the background layers are snapped. This is this checkbox. Okay, I now dimension the cross-section to determine the element thicknesses. I can do this via the symbols here. We have here several possibilities. I can do a linear dimension, arc length dimension, and so on. I choose here the linear dimension, and then I have to click or pick the points where I want to create the dimensions. I have to here to change the reference to the Y direction, and I do this also here for the flange projection in Z direction. I need this also here. And the dimensions here. And the dimensions here. I want to know which thickness is between the center point of the arc and this point here. For this, I create a help node. And then it's possible to make a dimension here. I think now I have all thicknesses so that I can now create the elements. The elements can be created graphically or via a dialog. The graphical input is called up via the symbol in the toolbar here. Here I have the possibility to define a single element or arc or circle. And the input via dialog is called up via the navigator data here, new element, single line, etc. When creating an element via the graphical input, the part is also created. If an element is created in an already existing part, this part will be extended if necessary. When creating an element via the dialog, the part and the points of the element must be created beforehand. Elements must be connected for the calculation of the effective cross-section. The connection is to be made via the start and the end points of the elements. If two elements share the same points, they are connected. I now define the elements via the graphical input, so I choose here this function single. Then I define the thickness 5.7 millimeters, and I pick the points on my background layer. Then I define the elements for the web. The web has a thickness of 3.1 millimeter. Same on the other side. Then I define the elements here on the flange. They have a thickness of 2.3 millimeters. I pick the corresponding points. Then I have to create the elements here. They have a thickness of 1.5 millimeter. Same on the right side of the cross section. Then I create the elements here in the middle. Then the connecting element here. And then the elements here. The cross section is now complete. You can see the subpanels here that were automatically being generated according to the rules of the standard that I have chosen in the base data dialog. Here it's a standard Eurocode 9. If this cross section is available in different dimensions, a parametric input is recommended. The parameterized input makes it possible to enter model data and internal forces in such a way that they depend on certain variables. These variables, such as length, width, or thickness, are called parameters. The cross section is in different heights, so I wanted to parameterize the height. The parameters can be defined in the global parameters, and I can open the dialog via the table, and here clicking on the symbol edit global parameters. First, I have to specify the name of the parameter in this cell. the name of a parameter must consist of ASCII characters and no spaces. The parameter is addressed in the formulas via the name, and each name may only be assigned once. I create a parameter called h1. This is for the height of the cross section. Then I have to define the unit group, and the unit group of the parameter determines whether the parameter represents a length, thickness, angle, etc. I can choose this in the drop-down. Here I define the unit group length, and the definition type controls whether the parameter is described by a value or a formula. Depending on your selection, you can enter the value or the formula in the following columns. I choose here the definition type value, and then I have to define the value, and this is 133 millimeters. Then I define the next parameter for the flange thickness. I call this parameter DF1, and I define the value 5.7 millimeters for it. Then I define the next parameter. I call it R1. This is for the radius, and I define the value 1.5 millimeter. Okay. Then I click on OK. I then define the coordinates of the top area using my parameters. The top area is this here. And for this, I go to the table points. And I see here I don't need this point. This point is not needed, so I can delete them. I go to Edit, select 3 points, and then I click on Delete. And now I want to parameterize all these points, so I select them, and then I go to this table function selected objects only, that only my selected objects will be displayed. I turn on also the numeration or the numbering of the points. And you have the option of addressing objects and their properties directly. For example, I can access the coordinates of points. If I want to access the coordinate of the point here, of the point 157, then I have to define this via the properties. A list of the properties can be opened via the menu View and then Console. And then here, if I click on the info button, then I see all object properties. Here I have the object property points, and the property coordinate 1 is for the y coordinate of the point, and the point I have to specify in this brackets. The coordinate 2 is for the z coordinate of the points that I have to specify in these brackets. Okay. I now define the coordinates depending on my parameters. I can do this directly in the table. For this, I want to define the y-coordinate of my point number 9. This is my point number 9. And to do this, I type in equal points 10 dot coordinate 1. So it's a y-coordinate of my point number 10 plus my global parameter R1 for the radius. I can show the formulas via this button, and it's also possible to define the parameters or the formulas in an additional window in the Edit Formula window. And here I define the z-coordinate of my point number 9. This is the z-coordinate of my point number 157. So points 157 dot coordinate 2. For the z-coordinate, minus h1 minus tf1 divided by 2. Here I see the result. Then I click on OK. It's also possible to copy the formula. So I open the dialog again, and then I copy this formula because I need this for the definition of my point number 10. For this, I open the Edit Formula window again. Then I paste this formula, and it's the same, but additionally plus R1. Okay. Then I define the z-coordinate of my point number 104. For this, I open the Edit Formula window again. And this is also plus R1. I do the same for the point number 105. This is the y-coordinate from my point 104. Minus R1. Okay. And this is points 147, the z-coordinate minus h1 minus tf1 divided by 2. Same here. But here it's plus tf1 divided by 2. Okay. Same here. This is only minus h1. And the same here. Okay, now I have to parametrically define the control points of my arcs, of these arcs here on the left and on the right. For this, I open the Edit Arc dialog via double-clicking on the arc, and then I can define the control point. For this, I open the Edit Formula window of the y-coordinate of my control point, and here it's points 9, coordinate 1, minus R1 divided by square root of 2. I copy this formula, click on OK. Then I have to define the Z coordinate. For this, I open the Edit Formula dialog again. And this is the Z coordinate of points 10. So I have to change it here. Z coordinate minus R1 divided by square root 2. Okay. I have to do the same for the arc on the right side. So I double click on this line, open the Edit Formula dialog, and I pass the formula. It's the y-coordinate of point number 105 plus R1 divided by square root 2. And this is the Z coordinate of point 104 minus R1. Then I click on OK. The thickness of the element must also be defined with a parameter. So I open the Edit Element dialog, and here I define the parameter for the thickness. For this, I open the Edit Formula window again and define here TF1. Okay. Now I've all defined all parameters, and for control purposes, I measure the height. For this, I create a linear dimension between the points 155 and 157. You can also add a dimension symbol if you activate the checkbox symbol, and you can also use HTML commands and special characters called entities. A subscript is achieved with a subtext. So if I want to define H and then 1 and subscript is sub 1 and then the end tag. Okay. Then I will show you the parameterization. For this, I change my parameters. So maybe here I change the height H1 to 80 millimeters. And if I go click on apply, you can see the result. I change it back to 133 millimeters and click on OK. I would also like to use this example to show you how to calculate stresses on the effective cross-section. In order to calculate stresses or the effective cross-section, a load case must be created first. Load combination can also be created. I create a load case via the navigator data. For this, I right-click on the load case and choose new load case. I define the name pressure and then I click on OK. Then I have to define internal forces. I can do this via the navigator data, or I can do this via the table. If I choose here internal forces, it's possible to define the internal forces manually. It's also possible to import the internal forces from RFEM or RStab via this button. Only import from RStab 9 or RFEM 6 is possible. The RFEM 6 or RStab 9 file must be saved with results for this. A load combination is supported as a load case, and I don't want to import internal forces today from RStab or RFEM. I want to define them manually in the table. For this, I have to enter the member number and the location, and then I define an axial force pressure minus 2 kilonewton. In the base data, I can make detailed settings. So I open the base data dialog again, and then I go to the tab settings and options. Here I can define if the stresses for elements should be determined in most unfavorable element edges or on element center lines only. And here it's also possible that an additional acting bending moment that results from the shift of the centroid of the effective cross-section relative to the centroid of the cross-section should be neglected. So I activate this checkbox and then I click on OK. Which stresses are to be calculated and output in tabular and graphical form can be set in the data navigator. Here under stresses, stress configuration, I open the corresponding window, and here you can activate or deactivate the stresses that should be calculated. Here the stresses sigma x total and tau total are activated. This is okay, and then click on OK. And then I'll start the calculation now. So I go to calculate all. And in the table, you have the results for the gross cross-section. This is here the thin-walled analysis. This is the sectional area for the gross cross-section, and you can switch here to the effective thin-walled analysis. Then the sectional area of the effective cross-section will be displayed. This is less than the gross cross-section, so I assume this cross-section has the class 4, and you can see this also in additional tables. Here you can choose the section classification, and I can see, okay, this is class 4, and I can see, okay, the subpanel number 2 is class 4. This is also selected here in the graphic, and I can switch also the graphical results to a thin walled analysis. This is for the gross cross section here, sigma x total, and I can see here also the effective cross section, and I can see, okay, the web is here reduced, and if I want to know the reduction, then I can go to the corresponding table. Here, reduced thicknesses. I click on the corresponding subpanel, and I see the effective thickness is here 2.4 millimeters. I can also set the display type in the navigator results. Here I can choose between isobands or isolines, and here I can choose the option off. And finally, I would like to show you the documentation. The printout report is structured in the same way as an RFEM 6 or RStab 9. You can create a new printout report using the data navigator. So I switch to the navigator data, and then I right-click on the printout report and choose here the option New Printout Report. Then the Printout Report Manager opens, and here I can activate the report items that I want to print in the printout report. Here I deactivate the unit stresses of the gross cross section. And if I click on Save and Show, then this opens the printout report. And this opens my printout report. Here I have all tables that I have selected before. It's also possible to print a graphic to the printout report. For this, I go back to our section, and then I choose print graphics to printout report. And here I can define the graphic pictures. This should be window filling. Then I go to Save and Show, and then this graphic will be printed to the printout report. If I don't want to have the numbering, I can go to Edit, and then I can deactivate the numbering, go back to OK, and the graphic will be changed. With the presentation of the documentation, I've now come to the end of my presentation. I will now give the floor back to Andreas.
Okay, thank you for your presentation. Nice presentation. I would like to show the attendees where they can find the recording. Just a moment, I hand over this or take over the screen. Okay, this is our website, dlubal.com, and under news and events and webinars, here you can find today's webinar and the upcoming webinars. If you click on it, you can see the event page, and in the next days you will find the recording in the middle here. You can find the presentation slides, the DXF files, and the model. Okay, and if you don't have already our section, you can use the trial version. Here above, you can find the link to the free trial versions of RFM6, RSTAP 9, and you can see our section here. You can try it for 90 days. Those are full versions. And you can use the model from this webinar or another model. We have got a lot of models on our website here under downloads and infos, the structure analysis models to download, RFM and RSTAP files, and also R section files. You can search for objects here, for example, the category or the product type. For example, our section search. That's today's model and some other models. Okay, just try it for free. I thank you for your attention. I thank Caroline for answering the questions or for your help with answering the questions. Thanks to Sonia for this nice presentation. I wish all a nice rest of the day. Maybe an additional information when you close the webinar, there is a small survey, only some questions. It would be very nice if you answer the questions. It's quite important for our quality management. I have to say thank you if you answer the questions. Okay, then maybe we see each other in another webinar. Bye-bye.